Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks section 13.7 titled Hamiltonian Cycles and Paths. Okay, so you saw in section 13.6, Euler circuits and Euler trails. Those were circuits and trails, where every single edge in the graph was used exactly once. You'll see that these Hamiltonian cycles and paths are going to be cycles and paths that use every vertex in the graph exactly once, except for the cycles where your beginning and end vertex will be the same because it's a closed walk, but every other vertex is used in the graph exactly once. All right. And it doesn't have to use every edge like in those Euler circuits and trails, as we'll see. All right, so again, the definitions. A Hamiltonian cycle in an undirected graph is a cycle, right? So that means it's it's a circuit, right? It's a closed walk that doesn't repeat any edges, but also doesn't repeat any vertices, right? That's what a cycle was. But it's a special cycle, right? It's a cycle that includes every vertex in the graph. All right, and then they go over the definition of cycle again. So therefore, every vertex in the graph appears exactly once in a Hamiltonian cycle, except for the vertex which is at the beginning and the end. All right, so that's a closed walk, right? A cycle. And then a Hamiltonian path, right? Remember what a path is from an earlier section. A path, remember a path was a trail, so no edges repeat, but also no vertices repeat. Right? And it's called Hamiltonian when every single vertex is used. Right? So a Hamiltonian path is in an undirected graph is a path that includes every vertex in that graph. Okay, so all the Euler stuff from section 13.6 included every edge. The Hamiltonian stuff here, Hamiltonian cycles, Hamiltonian paths, includes every vertex. So not necessarily every edge. For these Hamiltonian cycles and paths, you don't have to use every edge, just so that every vertex is in there. Okay, so note that a Hamiltonian cycle can be transformed into a Hamiltonian path by deleting the last vertex. Right? You just make it into an open walk and there you go. Therefore, if a graph has a Hamiltonian cycle, then the graph also has a Hamiltonian path. Okay. But not the other way around, as we'll see in a couple examples later. If a graph has a Hamiltonian path, that doesn't mean it's going to have a Hamiltonian cycle. Alright, so I'll play this animation here for you. They give you a couple examples of graphs. Like here, look at this graph here, 5 vertices. And start at vertex X, then they travel to V, to W, to Y, to Z, and then back to X. I ended where I started, so it's a closed walk. No edge was repeated, so it's a circuit, and the only vertex that was repeated was the beginning and end, so it is a cycle. All right. And what makes this a Hamiltonian cycle is that every single vertex in the graph is in it. Okay. This next picture. Again, all you have to do is take to make a Hamiltonian cycle into a Hamiltonian path, you just remove that last edge. See, all they did was remove the edge from Z to X. And here I have from X to V to W to Y to Z. right? It's an open walk, right? The vertex in the beginning is different than the vertex at the end. Every edge that's in the walk is only used once, so it is a trail. And every vertex is only used once, that's mentioned, so it is a path. And what makes it a Hamiltonian path is that every single vertex in the graph is used. All right, so just a couple examples, one of a Hamiltonian cycle, one of a Hamiltonian path. All right, so here's a graph here. So the questions below refer to this graph with, you got 6 vertices, A through F, and we're asked to, select the sequence that corresponds to a Hamiltonian cycle in G. Now, if it's a cycle, it's got to begin and end in the same place, right? It's got to be a closed walk. So right away, I can eliminate the second option, because this would be an example of an open walk, beginning at A and ending at E. So I'm down to 3 choices. Now remember I said too, if it's a cycle, the only vertex that gets repeated is the beginning and end. So maybe this one's okay. This one's a possible option. This one is not. The beginning and end are repeated, but you see another A in here as well. So this isn't even a cycle, this last one. Alright, so now I'm down to 2 options, the first and the third. And then again, in order for a cycle to be considered Hamiltonian, every single vertex has to appear in it, A, B, C, D, E, and F. Well, I'm not seeing vertex F in this first option. So without even traveling around the graph, I can tell you that the only possible option here that could be a Hamiltonian cycle is this third one. Now let's actually traverse the graph. Starting at A, I move to F, to B, to C, to D, to E, to A. And I just created a cycle, right? No edge was repeated. The only vertex that was repeated was the beginning and the end. So I have a cycle, and it's a Hamiltonian cycle, because again, every single vertex in the graph was hit. Now all I have to do to make that into a Hamiltonian path is remove that last edge from E to A. So make it A to F to B to C to D to E, and then stop. And there, I've created a path, right? No repeated edge, no repeated vertex, and it's an open walk. And it has every vertex in it. So just take this sequence here and remove the last A. So A, F, B, C, D, E, this one here, is a Hamiltonian path. All right. Now, this is something that's currently being studied in the field of graph theory. If you're interested in getting into it, maybe you could prove some results in the future about when Hamiltonian paths and when Hamiltonian cycles are guaranteed to occur in a graph. But that's not known right now, or at least at the time that this was printed. Remember in 13.6, Euler circuits and Euler trails. Remember a graph had an Euler circuit if and only if every vertex had even degree. And a graph had an Euler trail if and only if the graph was connected and there were exactly 2 vertices with odd degree. Right? The Euler circuits and Euler trails, you could tell right away whether or not a graph had an Euler circuit or an Euler trail. But unfortunately, there are no known conditions describing exactly which graphs have a Hamiltonian cycle or a Hamiltonian path. So for these pictures here, these whatever exercises you're given, you're just going to have to look at it and play around, try to find a Hamiltonian cycle or path. In fact, there is no efficient algorithm known that can determine whether a graph has a Hamiltonian cycle or path. Like there was an algorithm I went over in the 13.6 on how to create and construct an Euler circuit pretty quickly. There is no algorithm that's super efficient like that for a Hamiltonian cycle or path. A brute force algorithm could be used to find a Hamiltonian path, but that would enumerate, every possible ordering of the vertices and check whether the sequence they go through each ordering and see if each ordering is a path. All right. In the graph, this algorithm would take a very long time to execute on a computer, even on graphs of modest size. Like this graph here. There are 6 vertices. So if you looked at every possible ordering, remember that would be 6 factorial. There are 6 factorial ways of reordering 6 objects, 6 distinct objects. And 6 factorial is 720. So you would go one at a time through the 720 different orderings of the vertices and see which, until you come across a path. So you could go A, B, C, D, E, F. Oh, no, can't do that. Then how about A, B, C, D, F, E? Nope, can't do that either because it can't get from D to F, and so on. Right. Now, eventually you'd come across this guy here, A, F, B, C, D, E. Right. And that would be A, F, B, C, D, E. Oh, that is a path in this graph. Great, and it's therefore a Hamiltonian path because it has every vertex in it. But that's really the best we can do with at the moment with as humanity with computers. Again, like I said, this is currently being studied. I'm sure. People out there trying to determine if there's a way to ensure that a graph will have a Hamiltonian cycle or a Hamiltonian path. Now, we can't ensure that a graph has one, but we can in some cases. It can be proven that a graph with particular properties does or does not have a Hamiltonian cycle or path, but this is only in very specific cases. Not like the Euler circuits and trails. There was an if and only if. Of necessary and sufficient conditions to say if a graph has an Euler circuit or an Euler trail. Here they're saying, hey, there's only a few scenarios where you can say a graph will have a Hamiltonian cycle or path or not. So again, I'll play this for you. Graphs that do and do not have Hamiltonian cycles. So look at this first graph here. So they're saying, look, any closed walk that includes z and x must use this edge twice, shouldn't it? Right? Because I can't. If I start at z and I have the edge zx and I want a closed walk, I have to go back to z, so I'd have to use that edge twice. So there's no way to make a Hamiltonian cycle. Right? Because remember, a cycle never repeats any edges or vertices except the first and the last one. So what we can see here is that, if a vertex has degree 1 in your graph, you can't possibly have a Hamiltonian cycle. So any graph that has a vertex with degree 1 cannot have a Hamiltonian cycle. All right, this next graph. Remember, K5 is a complete graph with 5 vertices. That means every vertex has degree 4. Every vertex is adjacent to every other vertex. Right, called K5. And then you can select any ordering of the vertices. So they just put these 5 vertices in any order. And then copy the first and the end, and you can make it. Why? Because every vertex is, adjacent to every other vertex. There's always going to be a path from one vertex to the next, and then you just complete the cycle. So look at this. There's a Hamiltonian cycle here. And again, just reorder the vertices in any order and copy the first vertex at the end, and you've got yourself a Hamiltonian cycle if you're in a complete graph. Right? This procedure they went through here is only for complete graphs. Another word for this to remember would be 4 regular. Right? Every vertex has degree 4. Right. And then by the same reasoning, again, every complete graph, K3 or higher, K3, K4, K5, K6, etc., for the same reasoning will have a Hamiltonian cycle in it. And remember, if you have a Hamiltonian cycle, then you have a Hamiltonian path as well. Just remove that last vertex from the cycle. All right. So let's take a look at these graphs here and explain why they would or would not have a Hamiltonian cycle or a Hamiltonian path. Okay, so look at this graph here. Now you see vertex E has degree 1. So this graph cannot have a Hamiltonian cycle. Right? Because if I went to E and I try to get, so say I even started at E, right? I'd have to go E, D, C, B, A, and then to get, I have to get back to E somehow to create a cycle. But if I do that, I'm going to be repeating that edge ED. So again, vertex of degree 1, it does not have a Hamiltonian cycle. But I just showed you a Hamiltonian path. Go E to D to C to B to A, there you go. Every vertex is used exactly once. There's no repeated edges, right? And it's there, and that's it. That's a Hamiltonian path. Every single vertex was used. So this graph has a Hamiltonian path, but not a Hamiltonian cycle. All right, they went A, B, C, D, E, same thing. All right, that's a path. How about this graph? So again, let's just play around here. Now this is not a complete graph or anything like that. None of the vertices, have degree 1, so I can't say it doesn't have a cycle. So we're going to have to mess around with this. Well, let's see. I can see a path again. Just go A to B to C to D to E. There's your Hamiltonian path. Used every single vertex once on that path. But I can't get back to A from that path without repeating an edge. So let's see if I can find a cycle here. Maybe if I start, I can't really see a cycle, a Hamiltonian cycle. If I go B, again, in order to really do this methodically, I put these 5 vertices in all possible random orderings, 5 factorial, 120 different orderings, and then check through and see which one is a path. Which one is a path. Well, we can find a path. And I take all of those orderings and throw the first vertex on the end to make cycles, and then check every cycle, see if we have a cycle. Yeah, I'm not seeing one here. Here, B to C. Oh, no, I see one. B to C to A to D to E to B. There, that's a cycle. B to C to A to D to E to B. Yeah, I started at B, I ended at B, I used every vertex exactly once, except B, right, at the beginning and end, and no edges were repeated. So yeah, I found a Hamiltonian cycle in this. So this has both. All right, they did A to C to D to E to B to A, which is another Hamiltonian cycle in this. So yeah, it does have one. Okay, now this one, now these, just like with the Euler graphs, if the graphs are unconnected, you can't possibly have a Hamiltonian path or cycle. So the graph has neither, right? It's disconnected. Yeah, the only graphs that could possibly have a Hamiltonian path or a Hamiltonian cycle is a connected graph, one with a single connected component. This has two connected components. So I mean, yeah, there's a cycle here, but I can't possibly reach across to get every vertex in the same path or the same cycle. Alright, so I hope that all made sense. And then you have, your additional exercises. Some of these are assigned, some are not. Yeah, maybe all of them are. There's only 4 of them with a couple parts each. But again, if something's not assigned, I would still recommend looking at it, just for extra practice, extra exposure. You also have the solutions you can look at if you wish. Please, though, try to work on the problem first. Try to get it done on your own. Figure it out, before you look at the solutions. Because you're not going to learn anything if you're just copying solutions and not trying anything. Alright, I'm hoping this video is a reasonable guide through this section. Of course, if you have any questions at all, send me a message, and I'll get back to you as soon as possible. And thank you very much for watching.